Why do you think I like every yeah, but you guys have not in mind. I like your we are maybe like I did that one where it's kind of like 5 different goggles. Yeah. I don't know where they all have like wait. I swear. I saw it. Man, I'm using I see you do nice.
And I opened the application portal and it's like quick view updates and the view updates page is it's just blank.
I don't yeah. That's yeah.
I checked on my phone and I lost all my letters. It's like letters have like it's just a blank screen. I'm like, and yeah.
No, I get this like
I haven't heard of it.
You start there.
It would tell me the letter would be like.
Yeah.
Yeah.
They sent me an email like if you open your portal and it's on your there. And I was like, okay, and then I like look at it's like no.
Okay, good. Yes. Maybe like, hey, listen to this party.
Okay, guys, page 16. We're skipping over page 14 with open tolerance rule. I'll come back to this, but I want to cover this new topic first, and we'll revisit open tolerance rule if we have time at the end. If not, we'll push it to Monday. So I pronounce this Euler, but some students say Euler. I guess it really doesn't matter, but I pronounce it Euler like this. Euler's method. So this lesson, we're going to show how to find a solution to a differential equation. In this lesson, we're going to approximate a solution to the differential equation. This approximations method is called Euler's method. So remember how when we're dealing with slope fields, that the whole purpose of slope field is it can create a picture in terms of how the actual graph is being formed. And the main benefit of slope fields is especially when we're unable to solve that differential equation, because algebraically we just aren't able to separate the variables. And if we have all this the slope segments, then we can have an idea how the graph is going to move and how the actual graph is potentially getting formed. With Euler's method, the idea is that we're still using a differential equation, but we're going to have a starting point and a derivative equation, and we're going to just basically work our way to a given point using a bunch of linear approximations. So we're doing linear approximations across multiple steps in order to approximate a specific value that sits on the function. And this is based on the assumption that it's either hard to find the actual solution or it's impossible to find the actual solution, but we have the derivative formula in front of us, so we kind of inch our way towards our solution. I'm going to go through the first page, kind of showing us the process, but the way that I want us to do the problem is going to be more efficient, and that's going to be in a table form on page 17. But I want to kind of go through the the logic behind each of the steps, and then work out a much more efficient way once we understand the process. So we have a derivative equation of 1 plus y, and that's just going to be some slope formula. And then with this derivative, let's say the slope field is able to, let's say all the slope field was getting filled out. Okay, so we kind of have an idea based off of this slope field how the graph is going to move. And this is what the actual graph is looking like, but we're going to be based on the assumption that we don't have this in front of us, and we're just using the derivative to kind of help us inch along our graph. So we have a starting point. Our anchor point is 0, 0. And our delta x is 0.5. This is going to be our step size. So we're going to be inching along this differential equation by an increments of 0.5. Okay. So first off, we're going to construct a tangent line at 0, 0 for the interval from 0 to 0.5. So a tangent line equation looks like this: y minus y sub 0 or y sub 1 is equal to m times x minus x sub 1. So we know our order pair is at 0, 0. Our slope is coming from the derivative. So we can just plug the order pair into the derivative. Just going to indicate what I want to plug in. I want to plug in 0, 0. And 0 for x doesn't really apply. It's really 0 for y that the derivative requires. So 1 plus 0 is 1. So our slope is 1. So y minus 0 is equal to 1 times x minus 0. So our equation is y equals x. So with y equals x, we're going to find the next point. And if we're going through a step size of 0.5, then we're just plugging 0.5 in and finding the next order pair down the line. So the new point using our tangent line equation is going to be 0.5, 0.5. All right, we're starting at 0, 0, and our next x value is incremented by 0.5. So our next x value is 0.5. Plug 0.5 in, we get another y value of 0.5. Okay, so now that we have this order pair 0.5, 0.5, we're going to go through this process again, do another process of linear approximation using the same slope formula, and then inching, find the next slope, and then finding the next order pair. So we're just kind of repeating this process. So now we're going to construct a tangent line at 0.5, 0.5 for the next increment from 0.5 to 1. So again, y minus y sub 1 equals to m times x minus x sub 1. So we have our order pair that we want to plug in. The slope, again, is coming from the derivative equation. So dy dx. Now we're plugging in 0.5, 0.5. But again, looks like the derivative is only needing the y value, doesn't need the x. So 1 plus 0.5 is 1.5. Okay, so then we create our equation, y minus 0.5 is equal to 1.5 times x minus 0.5. I'm going to solve for y here, so I'll get 1.5x minus 0.25. Now we're inching up by 0.5, so then the next x value, we already have this point, so the next value over is at another 0.5. So if we add another 0.5, the next order pair that we want to figure out using this tangent line is at 1. So we're going to plug 1 into the equation. So we get 1.5 minus 0.25, and we get 1.25. So now we have this order pair. We're going to create another tangent line. So repeat the same process with a new order pair. And we'll end at 1.5 since that's the last step here. So construct the tangent line at this order pair. Again, the derivative slope formula only requires the y value because it's 1 plus y, so 1 plus 1.25, which is 2.25. Put into our tangent line equation. Solve for y. Again, the new x, so the new x is going to be now at 1.5. We already have this ordered pair at 1, so then the next increment over is at 1.5 since our step size is 0.5. And that gets us 2.375. So our order pair at 1.5, sorry. Our order pair at 1.5 using this incremental tangent line approximation across multiple points will get us all the way to 2.375. Okay, so here's the whole purpose here. The main idea with Euler's method is that we're using multiple tangent lines with updated slopes, and then the approximation of that point on the solution curve will be closer to the actual value. The smaller the step size, the more accurate the approximation. So if we're taking smaller increments, the derivative is going to help us give more detail in terms of, if we're taking smaller steps, we're going to have more accuracy. But if we're taking larger steps, then our accuracy will be less. We don't have to worry about, okay, how accurate is this Euler's method process versus another step size. We just have to be able to produce whatever approximation the problem is asking for, and that's really the extent of Euler's method. We're just basically using, just applying tangent line approximation multiple times across the same graph. So now that we see the big picture, we're going to have a much more streamlined way of gathering data. So a lot of what we're going to do is we're going to create a table, and we're just going to fill out that table until we get to our endpoint. Okay, next page. Okay, so here's a way that Euler method question could appear on the AP exam. They'll give you a derivative equation, slope formula. They say dy dx is 2x. Let f of x equal y be a solution to the differential equation. So we just know that the antiderivative is going to be some function, some f of x. F of 1 equals 3. So there's a starting anchor point. What is the approximation of f of 2? So we're trying to find f of 2. We don't have the function in front of us. All we have is the slope formula, but they want us to go through 5 steps of equal size. So the first thing is you want to find your step size. So your step size is going to be the formula delta x is equal to b minus a over n. So we probably recognize that from when we're doing our integrals unit and we're going through and finding approximations using Riemann sums. So that's the same formula there, delta x equals b minus a over n. Your a value is your starting x value, and your b value is your ending x value. So b minus a over n, a is 1, b is 2, and we're just doing the x value, so we're going to ignore that y value 3. Okay, remember, it's just going to be your x value. So it's going to be 2 minus 1 over, and they say 5 steps of equal size, so we want 5 intervals, so over 5. And we're going to get 1/5 or 0.2. I do want to point out something that I noticed last year in terms of when students were working through practice worksheets and quizzes, is that it's possible for step size can be negative. So if we're decreasing from our starting point to our ending point, then our step size should be negative. Okay, but here our step size is positive because we're starting to the left and we're ending to the right. Okay, so as long as you follow the formula b minus a over n, you're always going to get the correct sign. Just make sure you follow that process, but you don't have to worry about adjusting the negative. I think some students, they will just subtract the numbers and they'll just get the positive version of it and be done with it. So just be aware that it's possible for the step size to be negative if we're starting to the right and ending onto the left. Right? But in this case, step size is going to be positive. So next step is we're going to be kind of building these tangent line equations across, and this is a table you're going to create. Okay, they're not going to draw a table for you on the AP exam, but you're going to create your own table, and it'll be x, y, y prime, and then the new y. And the new y is going to be basically the tangent equation that you're going to build. So y prime is the same thing as your dy dx. It's basically just your slope formula. And then your new y is going to be y. You're going to find that by doing y sub 0 plus y prime times delta x. It's basically y equals mx plus b. It's just kind of rearranged in this form. So we recognize y equals mx plus b, but if you rearrange it, make it b plus mx. Your b is your starting y value, your m is your y prime, and your x is your delta x. Right. So, okay, so first, you're going to label, start off with your order pair. So your order pair is at 1, 3. That's your starting point. So go ahead and put those values down. And your step size is a positive 0.2. So you're going to keep adding 0.2 until you get to your destination. Thanks. Okay, so if I keep adding 0.2, I'll have 1.2. Keep adding 0.2, 1.4, 1.6, 1.8, and then we end with 2. So it says, find the approximation for f of 2. So here's our goal. Our goal is to get to this point. Once we get to this point, then we have our answer. We don't have to fill out the rest of this chart. So we're going to keep going from left to right, moving across these rows until we get to that destination. Okay, so now it's just a matter of just repeating the same process over and over again. Our dy dx is 2x. So we're just going to take whatever is necessary. In this case, our derivative only requires an x value. So we can just plug 1 in for the x, whatever the current x is for that row is. So in this case is 1. So 2 times 1 is 2. So there's my slope. My slope is 2, or my y prime is 2. All right, 2 times 1 is equal to 2. So now we're just putting it into this formula here. The new y value that we're trying to find, we're going to find that here. So we're going to say y is equal to y sub 0 is going to be the current y value that you're sitting on. So it's going to be 3 plus the slope is 2, and then your delta x is 0.2. And you'll get to use your calculator. Your calculator will get you 3.4. So now this is the new y value that you're going to transfer over to the second row. So now we're going to take this order pair, plug into the differential equation, into the derivative, sometimes the derivative requires more than just an x, or it may just require x and the y, or it may require just the y. You just have to plug in whatever is needed, but everything that you need is here. So if they need the x, you'll plug in 1.2. If they need the y, you'll plug in 3.4. Right? But in this case, our derivative only requires an x. So take the current x that you're on, 2 times 1.2. And this is my new slope. And put that slope into your tangent line equation. Take the current y value that you're sitting on. So now my current y value is 3.4. Plus y prime, my y prime, that's my current slope, 2.4. And then your delta x is always going to be the same. In this case, it's going to be 0.2. Plug into your calculator. Once you have your new y value, you're going to carry that down to the next row. And then continue repeating the process. It's not hard. It's just a little bit tedious, especially if you have to go through this multiple steps. But on the AP exam, on the quiz, I won't make you do more than 4 or 5. So that's the most. But if you're just once you get the first row down, you're just repeating the same process over and over again. Okay, so see if you guys can continue this process, and then you'll end here. Whatever number you get here, that's going to be your answer. That's going to be the approximation using linear approximation across these multiple steps. Euler's method will always just be an approximation. It's just, how accurate can we make our approximation? The more steps that we take, the more accuracy we're going to have. The less steps we take, the less accuracy we're going to have. But we don't have to worry about how accurate our approximation is. We should be able to find that approximation. I want to show you a couple different variations. I mean, it's always the same table that we're going to work through, but sometimes the problem is presented a little differently, and sometimes they give you the slope value without having us to plug in. So I want to kind of show you the different variations so you're familiar with that. Okay, let's look at bottom of the page, practice problem number 1. The table below gives the value of f prime, the derivative of f. If f of 1 equals 2, what is the approximate value of f of 2.5 obtained by using Euler's method with 3 steps of equal size? So All right, so first thing we do is go through and get our width, our delta x. Our a value is 1, our b value is 2.5, so b minus a over n. My n value is 3. Okay, so you're always going to be told your starting x value, your ending x value, and the number of steps that you're going to take. So looks like we're getting a positive delta x, since we're moving to the right from 1 to 2.5. Okay, so let's create our table. Always going to be 4 columns, your x, your y prime, or your dy dx, whatever the notation is, basically your slope. And then your formula that you're going to plug in. Y is equal to y sub 0 plus y prime delta x. Basically, point slope form or linear, point slope form or slope intercept form. All right, so start off with your order pair. We're gonna just go ahead and keep adding 0.5 until you reach your destination, so you kind of have an idea how far you need to go. So we're starting at 1, we're adding 0.5. We're gonna keep adding 0.5 until we reach that destination, 2.5. So at least we know how far we're gonna go before we stop. We're gonna stop here. We're gonna stop whenever we find the y value that's associated with 2.5. So we're not gonna worry about filling in those spaces. Right. So in this this table here, it's nice because we don't have to plug anything in. I mean, at least not until this part. To find our y prime, it tells us directly that our f prime at 1 is 0.3. So we don't have to plug anything in. It's telling us that information that the slope at f prime of 1 is 0.3. So we can just bring that value down. That's my y prime. So sometimes they may give you the differential equation. If they do, you have to go ahead and manually plug it in. If they give you a table of slope values, then you can just put that down without having to do calculations. Okay, so now let's get everything that we need from our table. Y is equal to y sub 0. That's going to be my current y value. Y prime, that's my slope. And delta x is always the same. In this problem, it will always be 0.5. Use your calculator. And whatever y value that you get, that's going to be the y value you're going to carry to the next row. Okay, so now we want to find the slope at 1.5. Our table does provide that for us. The slope at 1.5, f prime of 1.5 is 0.7. Tangent on the equation to get our new y value. So we need the current y value, which is 2.15, plus y prime, the current slope, and delta x. Whatever y value that you get, bring that over to the next row. We have one more row to get through. Now we want to find out the slope at 2. Slope at 2, the table gives us 1.2. And then go through our process one more time. And there's our answer. And let me just show you one other variation, and then we can move into L'Hopital's rule. So on page 18, can we look at number 5? Okay, page 18, number 5, bottom of the page. Okay, so let h of x be the definite integral from 1 to x of root 1 plus t squared. Use Euler's method starting at 1 with 2 steps to approximate h of 3. So we have our a value at 1, we have our b value at 3, and then 2 steps, so that's going to be our n value. Okay, so let's start off with delta x. B minus a over n. Start off with your chart. Now we're going to have to build our h prime on our own because we have h of x. So h prime, guess what we have to go through here? What does that look like to you? Yeah, second theorem, right? We know that h prime is the derivative of this definite integral. Anytime we're undoing the integral, they're going to cancel out. Just plug the x in. We're not going to change the function because the operations will cancel each other out. So just root 1 plus t squared, or sorry, root 1 plus x squared. That's going to be my h prime. Okay, so that's the formula that I'm going to use to build my derivative or my slope. And then your last column, y prime, h prime, these are the same, but that's just basically slope value. Okay, so we're starting at 1. Oh, they're not telling us the y value. How do you think we can find that y value? Yeah, plug it into the original function, right? So if I plug 1 into the upper bound, what do you know about your integral if your upper and lower bound are the same? Just 0, yeah. So all right, so derivative only requires the x value. So, oh, sorry, let's do our delta x and make our way down to how far we need to go. So our step size is 1, so we're going to keep adding 1 until we get to 3. So just 2 steps, right? So if we stop here, then we're done. Okay, so into h prime. H prime requires the x, plug 1 in for x. 1 plus 1 is 2. Root 2 is my slope. So slope goes in for y prime. Y sub 0, that's going to be my current y value. Y prime, that's my slope. Delta x, that's my step size. Once you have your y value, carry that to the next row. Repeat the process again. H prime now requires the current x value. Current x value is 2. 2 squared is 4. 4 plus 1 is 5. So my slope is now going to be root 5. Current y value is root 2. Slope is root 5. Step size is 1. So root 2 plus root 5. Whatever that decimal value is, we'll just leave it like that since this is the exact value. So we can just say h of 3 can be approximated to be root 2 plus root 5. Okay, hopefully you guys find this pretty easy. It's a little tedious, especially if you have to go through the multiple rows. But as long as you know how to set up your table and your chart and your delta x, it should be pretty straightforward. Just be aware that sometimes delta x is negative. If delta x is negative, you have to make sure that you multiply, that you're putting in that negative value for delta x. Your homework will come from page 19. I'm just going to assign 2 problems to do. This is all the same process, but I'll identify those 2 problems at the end. Let's go back and talk about L'Hopital's rule, at least revisit it from a different perspective on page 14. Okay, page 14, L'Hopital's rule. We know that the whole point of L'Hopital's rule is involving limits. And if the limits of an expression gives us 0 over 0 or infinity over infinity, we know that gives us the green light to take the derivative of the numerator and denominator and then reevaluate the limit. So far, we've just seen it as a shortcut for the limit process that we learned at the very beginning of the year, where if we get 0 over 0, it's a lot easier to find the derivative. It also works for infinity over infinity, but we haven't explored this. The reason why is because it's a lot faster to just compare degrees and get the limit, get end behavior, and it's faster than having to go through the whole derivative process. So, but now we're going to see some examples where we may have to deal with this infinity over infinity. So the rule works great, but for now, at least for us, it works for the form of 0 over 0 and to a lesser extent, infinity over infinity. There are other indeterminate forms that involve, that looks like this, either 0 to the 0 power, 1 to the infinity, infinity minus infinity, 0 times infinity, or infinity to the 0. So anything involving exponents of 0 and infinity is usually considered also other forms of indeterminate. And we can still use the rule for L'Hopital's for these scenarios, but we have to first convert them to be numerator and denominator so that we can visually see either 0 over 0 or infinity over infinity. So sometimes we have to do some algebraic manipulation to get the form to be numerator and denominator so that we can get these scenarios to show up. Okay, so our goal is we're trying to get a problem to show us 0 over 0 or infinity over infinity, especially if the numerator and denominator is not quite in that form. But once we get into the correct form, get that 0 over 0 or infinity or over infinity, then the rest is just L'Hopital's rule. Derivative of the top, derivative of the bottom, and then reevaluate your limit. So let's look at a couple of examples here. So let's start with example 1. So limit as x approaches infinity. The idea is, well, if we want to do L'Hopital's rule, we really would like to get a numerator and denominator to show up. So the root x is already in the numerator. The e to negative x, this is an easy one that we can rewrite in a denominator with a positive exponent. So these are the same. And if we plug in infinity, we are going to get infinity over infinity. And that is a form for L'Hopital's rule. Now, there's another way that we can do this. The faster way that we can do this is going through comparative growth rate, seeing that your denominator is growing at a faster rate than the numerator, and you know that's just going to zero out. But let's just go through L'Hopital's process here. So because we're getting one of the variations of requirements for L'Hopital's rule, we can find the derivative of the top, derivative of the bottom, and then reevaluate. So derivative of the top, root x, the same thing as x to the 1/2. So 1/2 x to the negative 1/2. E to the x, just e to the x. And then reevaluate the limit. If I clean this up, I'm going to get 1 over 2 root x e to the x. And this is pretty obvious that if my denominator is growing to infinity, this fraction is clearly headed towards 0. Okay, let's not worry about part B. Let's go to example 2a. So we're involving a limit. You have a variable raised to a variable. So the idea is, well, this is going to be a lot easier to manage if we can somehow bring that down so that we can work towards getting a numerator and denominator over each other. In order to apply L'Hopital's rule, we really need to see that numerator and denominator clearly giving us a 0 over 0 or infinity over infinity. So the way that we're going to approach in dealing with that exponent is we're going to try to bring it down. But to bring it down, it's a lot easier to bring it down if there's logs involved, because we know we have log properties. Log differentiation, log properties will allow that exponent to come down. So let's think of our function as 1 plus 2 over x to the x. So we're going to be working with this expression until we get to something that can be more manageable. So if we introduce logs into the problem, then that x can be have an easier time to come down. So we'll take the natural log of both sides. Now that we're inside a log expression, that exponent can be free to come down. So the idea is we would like to focus on this portion of the problem. Is there a way that we can find the limit of this? As if we can somehow get this to look like a numerator over denominator, we're going to have a much easier time working our way to applying L'Hopital's rule. So if I want to force that x to be in the denominator, I can make it x in the numerator, same thing as x to the negative 1 in the denominator. Okay, so I'm trying to really force that numerator denominator to show up so that I can get my form to fit with L'Hopital's rule. Now, x to the -1 in the denominator, same thing as 1 over x in the denominator, right? So if I plug infinity in for x, this will go to 2 over infinity is 0. Natural log of 1 is 0. So I'm going to get 0. And then infinity into the denominator. That's going to cause this fraction to get smaller and smaller. So that's also 0. So now we have something that has the requirements for L'Hopital's rule. So I'm going to get my expression ready for my derivative process. So both terms are now ready for me to jump into the derivative because once we have 0 over 0, we're free to do L'Hopital's rule. So the derivative of natural log of u is u prime over u. And then the derivative of x to the -1 is -1x to the -2. So this is a little messy here, but I'm going to try to resolve this complex fraction. Dividing by a fraction is the same thing as multiplying by the reciprocal. Okay, your homework, it'll just be 2 problems from page 19. I'll send out a reminder. It'll probably be like, number, oh wait, we still have time, right?
Yeah.
My bad. Sorry, we still have time. I think they messed up on the bill schedule. Unless, I don't know if they're going to announce it.
Is it a C schedule thing?
It should be A schedule. Well, if everyone is leaving, then we'll have to go. Okay, but I'll send out a reminder tomorrow about our your homework problem.
Okay, you flip through and then okay, appreciate it. Thanks. And then this is mine.
Got it. Thank you. They're just 9, 10 and 12. Thank you. I see you.
It was really bad. It was like before midnight, and I was like going in.
Have a good weekend.
Thank you.
Have a good weekend.
Hey, thank you, Logan.